السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الرابعة إن شاء الله زينين. محاضرتنا لهذا اليوم هو Best Approximation. Suppose that S is equal to phi 1 until phi n is an orthonormal set. Orthonormal system. Suppose this is orthonormal system for V another product with this. Consider the linear combination summation I from 1 to n alpha I phi I for arbitrary alpha I belongs to complex number C by the best approximation of any phi belongs to V through the given orthonormal system we mean, this is what mean best approximation. We mean a particular choice of the alphas, minimizing the norm phi minus summation I من 1 إلى n alpha I phi I. In what follows, we determine the page number 1. We determine the optimal choice for the scalars alpha I. Observe that norm of phi minus summation I from 1 to n alpha I phi I square. This is equal to, this is right here and here, phi minus summation I from 1 to n alpha I phi I, and also here phi minus summation I equal 1 to n alpha I phi I. And this is inner product. This is equal to inner product phi is first one, this is first one here, phi minus inner product phi with summation and here should be take j because this is different. Here I and here j, and here j, and here also j. And now this is j is equal to 1 to n alpha j phi j minus inner product summation I from 1 to n alpha I phi I, and this is phi, and this is a plus inner product summation I from 1 to n alpha I phi I, and summation j from 1 to n alpha j phi j, and this is will be equal to, will be equal to what? Equal to norm of phi square for this, and this is minus. Here we can move summation and alpha j out of inner product. It will be summation j is equal to 1 to n alpha j conjugate here, because this is on the right side, so go out is as conjugate, and this is phi j minus here minus summation I from 1 to n alpha I, this is without, and here without conjugate, and here alpha I phi plus summation I from 1 to n alpha I summation j from 1 to n alpha j, and this is phi I phi j. Since this is delta ij, why? Because since phi I phi j orthonormal, so this is 1 0 1. If I equal j, so this is 1. If difference, so this is will be 0, and that means this is will be equal to norm of phi square minus summation j from 1 to n alpha j alpha, here it will be I conjugate phi I minus summation I from 1 to n because we take I equal to j now. Now in this step we take I is equal to j, and this is alpha I. We can change phi I and take conjugate. Change this here, move this here and take conjugate. This is will be plus 2 summation I from 1 to n absolute value alpha I. This is power 2, and this is, we call it double star. This is double star. On the other side, absolute value phi I minus phi I minus alpha I square. Here there is inner product here, minus this will be square, is equal to, of course this is will be phi I minus alpha I times phi I minus alpha I, and this is conjugate. This is by definition of complex numbers. And move this is to both this and this. This will be the same phi I minus alpha I, and this will be phi I conjugate minus alpha I conjugate. Move this here and here, and now we can move this here and here, and this here and here will be phi I times phi I conjugate. Yes, and this alpha I conjugate times phi I minus alpha I phi I conjugate plus alpha I square. This is page number 2. And now we can say that this is will be equal to alpha phi I square, because this is the same, and this is from definition of complex analysis, and this is minus alpha I conjugate phi I minus alpha I phi I conjugate plus alpha I square. Hence you can move here. Now you can get minus alpha I conjugate inner product phi I minus alpha I phi I conjugate. This is this and this, and move this and this to other side, no, sorry, just this, plus alpha I square, and move this one to other side. Here, this is equal to alpha phi I minus alpha I, this is square, minus inner product phi I, all square. We move this to the other side. We start from this. Look, remind you, we start from this, and all of them equality, and here this is the last equality. Just move this here, so we can get now this is equal to this minus this. This is clear. Therefore, we can write double star, that is, as this is double star, this is double star, and this is equal to this. This is equality here, and here is equality, and here is equality, and here is equality. So this is equal to this, and we can write it another way. Inner norm phi minus summation I is equal 1 to n alpha I phi I square. This is equal to norm of phi I, norm of phi square minus summation I from 1 to n phi I, this is square, plus summation I from 1 to n inner product phi I minus alpha I. This is square. How can I write this? We get, look, this is equal to this. Yes? So, and this look like this, look this, and this, and this is look this, and this look this. So we can substitute, and this the same. So we can substitute here in double star. So we write this is equal to this is equal to this. This is equal to this. So sum of this also is equal to this. So substitute summation this and summation this, because this here is equal to this, and substitute in double star. So this is clear. Hence, now phi minus summation I from 1 to n alpha I phi I can be minimized whenever alpha I is equal to phi I, for all I is equal to 1 to n. This is here is equal to this, and hence this equality can be minimized whenever alpha I is equal to phi I. Can be minimized whenever alpha I, this alpha I, is equal to this. Alpha I is equal to this. So this will be 0. If this equal this will be 0, and this will be minimized. Look. And we obtain the so-called Bessel equality. Bessel's equality. This is equality, this norm of phi minus summation I from 1 to n phi I square is equal to phi square minus summation I from 1 to n inner product phi I square. This is Bessel inequality. If we want to minimize this, we take phi equal this, phi I is equal to phi inner product phi I. So this will be moved and this will be 0, and we take this and we call this equality Bessel equality. Call this Bessel equality. This is page number 3. And since phi minus summation I from 1 to n phi I, this is square, this is greater than or equal to 0. This is positive because this is norm. So this is greater than 0. We also get the Bessel's inequality here. Inequality. We also here get this is Bessel inequality. Look, this is positive and this is equal to this. This is positive and this is equal to this. So also this is positive, more than 0. This is more than or equal to 0, and also this is more than or equal to 0. So we get the Bessel inequality look like this. Summation I from 1 to n, absolute value phi I inner product square less than or equal to norm of v square. This is star. This is Bessel inequality. This is Bessel inequality. The Bessel's inequality allows us to extend our treatment. Our treatment to infinite orthonormal system. Not just to infinite, finite, but even to infinite treatment systems. Indeed, since norm of phi less than infinity for all phi belongs to v, we can take the limit for n goes to infinity in a star. This is a star. You can take this is goes to infinity and conclude that summation I is equal 1 to infinity phi I and our product square. This is less than infinity. This means that inner product phi I belongs to n. This is a sequence. Is a sequence in L2 for all phi belongs to v. It's page number 4. Hence, an orthonormal system induces a map from V to L2. At this point, it is tempting to think that given an orthonormal system in V, we can express any element in V as a suitable expression over the phi's phi summation approximation I from 1 to infinity phi I. This is generalized Fourier series of phi, and phi I, this is generalized Fourier coefficient of phi, and this is called double star. In double star, we did not use the equality. Symbol, but the approximation symbol. For this is page number 5. For two good reasons. Number one, we don't know whether or not this series converges. Number two, we don't know this is series converges or not. Number two, if the series converges, we don't know if it converge to phi or to some other element in V. I think this is enough for today. Thank you very much. This is page number 6. I think this is 6. Yes, this is page number 6.